different parameters in there, and what is the importance of those hyperparameters, not the parameters, hyperparameters we need to understand. So there are many parameters here, number of layers, number of units, right, in each layer, and the learning rate decay or the learning schedule, and beta 1 momentum hyperparameter, and RMS prop hyperparameter, epsilon. Right, these are all different parameters there, and regularization is also there. Right, on a logistic regression node, we generally do regularization. There is a shrinkage parameter lambda, right? So that parameter is here also. Basically, we are using the gradient descent algorithm, right? So all those parameters will come. Along with that, we have additional number of layers, number of units in a layer, right? These betas, right, epsilon, these hyperparameters are there. And then we need to understand what is data augmentation and how it can actually help. Okay, so data augmentation means you have one picture of a cat or a dog. We can create multiple pictures by rotating them a little bit, right? Tilting them a little bit and rotating them a little bit, so that it will actually, the model will understand that all those pictures are related to cat or dog. Okay, so data augmentation, how it can help and all that we'll understand. Activation functions we already understood. Normalizing input and what is the use of it, and vanishing and exploding gradients and optimizers we'll learn. Okay, so in a machine learning setup, we'll generally take 80% as the train set and 20% as the test set. But in deep learning, right, it is not always like 80-20 or 70-30. You take 10,000 records. Generally deep learning algorithms need a huge volume of data. You take small chunk, maybe 10,000 records aside, and put them as a test set. Rest all you use for training. It is not always that 80-20. I think we already know this. I already explained it. So there are shallow neural networks and deep neural networks. These two are the shallow neural network examples. Only one hidden layer or no hidden layer at all. See, this is a normal logistic regression function, a logistic regression algorithm. One logistic regression, you are passing your input, and you have y cap, and that is also can be called a shallow neural network. And one hidden layer is there, that is also called as shallow neural network. Okay, one or less hidden layers, shallow neural network. More than one are called as deep neural networks. Okay, any neural network is called as artificial neural network. So this is terminology. No need to be worried. So in our machine learning, right, there is bias variance trade-off. When I say bias variance trade-off, when bias is high, variance is going to be low. When variance is high, bias is going to be low, right? Overfitted model, underfitting is going to be less. Underfitted model, overfitting is going to be less. But in deep learning models, right, you can have both at once. Okay, high bias, high variance, and high variance, low bias and low variance, both can be present at once. Okay, so on the train set, the error is 1, right? On the test set, the error is 7. That means it's a high variance model, overfitted model. Model is working good on the train set, not working good on the test set. That is overfitting. Okay, and on the train set you got 12 as error, and the train set 13 as error. Right? If you look at accuracy, right, it's going to be 88, 87. So model is not working good on the train set as well as test set. So this is model is not working on the train set. So high bias model, underfitted. Anyway, it will not work on the test set also. Okay, and then high bias and high variance issue, right? Model is not working well and on the train set, and it is working worse on the test set. Okay, so that is high bias and high variance model. So model, first thing is that on train set it is not working well. When you tested it on test set, even worse. The gap is less here. The gap is high here. So you can say that is a underfitted and overfitted both at once. Okay, you can, like in this case, right, on which area you focus first is try to fix the underfitting. Okay, so model should work well, right? Model should work well first, and then you try to reduce the gap between train set and test set by regularizing. So why we are looking into these? Because regularization I'm going to talk about. So when do you do regularization? Model is underfitted, you do regularization. In this case, and in this case, sorry, model is overfitted, you do regularization. In this case, you do regularization. In this case also you do regularization. Here, the model is working good on the train set, good on the test set, right? So this is the best fit model. Okay, this is the best fit model. So gap is also less. If gap is more, we would have said overfitted model. If it is 1 and this is 10, then we would have said overfitted model. This 1 and 1.3 gap is less, so it's kind of model is working good. Even here also you can apply regularization to bring the gap less. In regularization, you are actually trying to make the model a little weaker on the train set by reducing, by increasing constraints. Increasing constraints means increasing the lambda value will make the model underfitted. Decreasing the lambda value will bring it to the place where the model was actually, right? The overfitted model where it was. So the point here is, in deep learning you can have high bias, high variance both at once. There is no trade-off concept here. And where you focus on is the important thing. Here you try to fix underfitting. Here you try to fix underfitting. Right? Here you try to fix overfitting. Got it? Any questions? So how to address overfitting? There are two ways. You can reduce layers, you can reduce nodes, right? Manually. Right? Yesterday I did it. On a big network, I actually took only 4 nodes and it started working. That may not overfit on the train set, sorry, test set. Right? So you can do that, or you can use L1, L2 or dropout regularization. A new regularization concept called as dropout regularization also will learn in the deep learning. So generally these deep learning models are built to achieve human level performance. Okay. So how do you decide a model is underfitted or overfitted? Right? I said, when I get 12 as the error, 12 as the error, I said it is underfitted. How do you know? By looking at the human performance, we'll know, right? Humans are bias error. This is actually human error, okay? And then this is training error. This is cross validation error, and the avoidable bias we call it as. Which one to focus on, right? Here, when I looked at 12 here, I said I need to focus on underfitting. How did I decide? On the same data set, if a human works, if he gives only error one here, that means the model is not actually matching human level performance. Okay. Avoidable bias is a term which is used to measure, on which area to focus on. Okay. See here. Suppose that there is a person identification model. Right? You show a picture to the camera, and it need to identify the person. Right? Human beings can do it very well. Right? So human beings, give me 1 second. Focus. Yeah. So this is one example, right? 1, 8, 10, 7 is one example of a model, one model, and this is another model. Okay, 7.5, 8, 10, and 0.5 of another model, scores of another model. So human error on the first model is first data set is 1. That out of 100 pictures, human is identifying 99 correctly, 1 wrong. On training set, right, it is actually getting 8 as error. On cross validation, it is getting 10 error. Right, the avoidable bias is 7. Right, if you look at this, that on training set it should have performed better first. And the difference between 1 and 8 is 7, but the difference between 8 and 10 is 2. So on training set and cross validation set, the gap is not that big. But on the human level, human bias error and then the training error gap is high. So we should be focusing on the 7 score, or the the model is underfitted. We need to make the model overfitted. Did you get it? On a particular data set, if the human level performance is 1, then we should be focusing on or underfitting problem. Underfitting problem. Did you get it? Especially in deep learning models, we try to achieve human level performance, not in the machine learning algorithms. That's where we are comparing the model's performance with human level performance. On a second data set, right, the human is making 7.5 error, but model is making 8 error, right? And then the cross validation is 10, right? Here we can say that the gap between the training error and the cross validation error is high compared to the human level error and the model's error. So you should be focusing on overfitting, right? Focus on variance. We should focus on overfitting. To reduce overfitting, what we need to do? We need to apply some regularization. These kinds of models, right, we apply regularization. Till it reaches this place, we try to make the model as complex as possible to reach to human level performance. Will we get all the time? No, no guarantee. Okay, especially in NLP projects, right, you will not get too good performance there. There are drawbacks with existing models also, but still we do AI because it is evolving. Maybe in 2 years, 3 years, we'll get nice data sets and the representations, word vector representations kind of thing, which will make the models work better. So any questions here? Human level performance? And how do you identify whether a model is underfitted or overfitted?
Yes, sir. And the human errors is how to really measure it, sir? Maybe just by taking some sample. Is that so?
Generally, we know, sir, right? Yeah, generally, sample is one thing, right? Yeah, that's a good question. When you get a data set, right, first thing you need to do is manually verify the data, right? While manually verifying the data, you will know how good you are doing, or a business analyst is doing. Generally, as a data scientist, if you have to work on an NLP project, you need to read through maybe couple of hundred documents and try to prepare a data set or do some activity parallelly. While doing that, you need to read through the documents so that you will understand the pattern, right? So while doing that, how good you are in identifying things will decide human level performance, right? So I was looking into one of the use cases most recently, and there we need to extract some things like headings kind of a thing, right? In some documents, right, there is no heading. So when you read through the email or that whatever document, you may not be able to find out heading for everything because you may not know the business, right? In that case, right, human level performance is also going to be 80%. But in another data set, if you have heading in all the documents clearly mentioned, maybe a side heading or a center of the document, you will be, or maybe in first 2 pages are preface and the third page or fourth page you have heading, then also you will be able to identify. There it is 100% performance. So manually we verify the data, and then while verifying data, we'll try to prepare some training set or kind of thing. That time you'll know human level performance.
Okay, sir.
What you said is true. Sample only. We'll take sample and try to play with it, because business, the client will give us some data set. They are familiar with that data, but we are not. We need to get familiarized with it and then start doing AML models. It is just that what human being is doing while identifying a person or while identifying an entity or while identifying a heading. The same thing we will try to make it happen with the machine learning algorithm. That thing we should remember, right? Whatever we are doing, we'll try to make it happen with the machine learning algorithm. Okay. So that's a good question, and I think you got clarity on that. So now we'll see L1, L2 regularization. Okay, L1, L2 regularization. So L1 regularization, lasso and ridge L2 regularization, right? Ridge regularization, when you apply, it will not make all the coefficients 0, right? It will actually keep some coefficients which are even when they are not that important, some coefficients it will try to keep them, right? That is ridge regularization. Lasso regularization is will drastically reduce the weights towards 0 when, especially when the feature is not important. Okay. In deep learning, what it does is it does the same thing. It actually is trying to reduce some of the weights to close to 0. Some of the weights close to 0. When some of the weights become 0 or close to 0, a particular node may completely vanish, or a particular node's importance will reduce. Do you agree? I made a statement. When some weights are becoming 0, or some weights are actually coming close to 0, a particular node may completely vanish, or a particular node's importance may reduce a lot. Right? Example is that 3 weights are coming in, right? When I say 3 weights are coming in, we are multiplying this weight with x1, this weight with x2, this weight with x3, right? Suppose that x1, x2 weights, the w1, w2 have came close to 0. Only x3 weight is there, maybe that's also very close to 1 and less than 1. Then what happens? This whatever linear combination is going to be less, and the calculated output is going to be less. Unfortunately, if all the weights come close to 0, then the linear combination is going to be very close to 0, and it is maybe positive, maybe negative, right? It's going to give you a very less probability. Right? Again, this less probability, even though there are weights here, right, bigger weights here, it is going to nullify the effect of this node. If this node is outputting a number which is close to 1, then all the weights here going out will have importance in the next layer. If this node is outputting a number which is very close to 0, the weights going from this node will not have any effect on the next layer. Got it? That's like vanishing this node. So when you apply regularization, it will actually try to make these weights kind of close to 0. Got it? How regularization works on a deep learning model.
So this vanishing happens only on lasso.
Lasso, number of nodes vanishing or number of nodes reducing the importance will be more. Rigid is going to be less. Less number of nodes will vanish in rigid. More will vanish in lasso. Okay. So I have taken an example here. For example, explanation purposes. Let's take sigmoid function as activation function. When regularization parameter is too big, weights will be small and close to 0, right? Weights will be small and close to 0, right? Z value is also going to be small, making the sigmoid curve a straight line, right? So a sigmoid curve becoming straight line means the node becoming linear equation, right? Some nodes will become linear equations, just the linear equation. Okay, when some nodes become linear equation, right? All those nodes will be outputting the same thing. In a neural network, if you use linear nodes as hidden nodes, even if you use 100 nodes or one node, it will give you the same output. That's the thumb rule we have actually learned, right? So the same concept will apply here. If they are sigmoid functions, when z value is very close to 0, right? The outcome, right? So the weights are high. So sorry, the regularization parameter is high, right? The weights are going to be low and z value is going to be low. Weights are going to be low, z value is going to be low. Z value means linear combination is going to be low. For many iterations, the same linear combination comes or the similar linear combination comes. The g of z also going to fall in the straight line rather than in the curvy areas. When the activation functions are non-linear, then only you will get a different outputs and model will be a bit complex. Okay? When you are actually intentionally making some of the nodes linear, the outcome, the model's complexity will reduce because some of the nodes have become linear and they are trying to output the same thing. Okay, instead of it is like even though you have 4 nodes here, it works like one node because all nodes will be outputting similar output. Got it? Got it? Any questions? So now we can actually apply this regularization. Let me show you the code here. You can execute anyway. I did not install TensorFlow on Windows machine. But we can look at the code and tomorrow I'll execute. See, somewhere I applied regularization. Drop out this. I think in callbacks, I think I implemented that. Let me try to. Okay, so here, see this kernel regularization. There are two, regularization in densely in dense layer. API will change always, right? So kernel initializer, Glorat uniform. We'll talk about this initialization, right? In just maybe today itself we'll talk about it, I think. Okay, and bias initializer and kernel initializer. Okay, bias initializer is zeros by default. That means they are not taking one, one as bias. Okay, kernel initializer, right? Kernel initializer, bias regularizer and kernel regularizer. There is an activation regularizer also. I don't know what this activation regularizer. Let me see. So activation regularization function applied to the output of the layer, output of the layer. It's activation. Kernel constraint function applies to kernel weight matrix. Okay. Okay, there are two different ways of applying, constraint, kernel constraint, bias regularizer, kernel regularizer. Okay, got it, got it. So, if in a neural network, right? So, on a normal logistic regression or linear regression, how are we applying regularization on the cost function, right? On the cost function, we are adding additional term. Let me open that. See, this is how we are applying, right? So we have taken the cost function and then additionally we are adding this additional term, right? So when you play with this lambda, the model will actually go, work like, if you take lambda is equal to 0, it's going to be same as the original overfitting. If the lambda is equal to 1, it's going to be highest um, uh, regularization. So it's going to come down to biased model, right? So that's how we are applying regularization here. And the deep neural network, there are many nodes here, okay? And you are taking the output from here, and then you are taking this y cap here and then applying the regularization. Okay? So MSE will have that cost function, right? That cost function, right? It's going to be minus phi log h of x, minus 1 minus phi log 1 minus h of x plus whatever this, right? Whatever this regularization. So in this, right, there are outcomes from the nodes here, and there are weights going into the nodes. So in deep learning, there is a facility to apply regularization on the weights only and on the outputs only. So here we are applying regularization on the total model, I think here, right? Total model. And I'm actually thinking right now. No? So when you apply regularization on these outcomes of the nodes, right? You actually, so not only the weights you are constraining, you are actually constraining the outputs of the nodes also. How it is done? Equations I have to look for, but in a deep learning model you have two parameters there, right? Two parameters. One is kernel regularizer, activation regularizer, right? Kernel regularizer, we know what is kernel. In a deep learning, kernel means weights. In a deep learning model, all these weights are called as kernel. And this kernel matrix, these are all, there will be a kernel matrix here, there will be a kernel matrix here, there will be a kernel matrix here, kernel matrix here. So when you apply regularization on a normal linear regression or logistic regression, it is going to constrain the weights. No, if the lambda is too high, it's going to reduce these weights. Lambda is too low, it's going to keep the weights as it is, weight matrix as it is. But in deep learning, right, you can control the outcome also. These outcomes, should I be reducing or should I be increasing? Got it? So to constrain these outcomes, right, you can use kernel regularizer. Sorry, the activation regularizer. Got it? Got it, right?
So when the weights are regularized, automatically the output will also be changing, right?
Output will change. Output will change. That's where the model will, become a little weaker.
Then why the activation regularization is required and how it is different?
Maybe, I don't know, but it's a black box basically, right? Maybe sometimes regularizing activations will also, maybe model is too much overfitted. You are applying weight regularization, still it is not coming down. Maybe you need to apply regularization on activation functions also. This is a new parameter, I see, right? New parameter it is, and generally weight regularization is the one we use. And frankly speaking, dropout regularization is the one we actually use most. Okay, so frankly speaking, I don't know. It's a black box how exactly it happens. But when you reduce the weights or the activation values, model will become weaker. Our goal of regularization is to make the model weaker so that it works well on the train set and test set. Got it? I don't know. Maybe I answered it completely or not, but did you get the the idea behind it?
Yes.
Yes and no, maybe, right? That's fine. So here, right, you can apply kernel regularizer, right? There is a tf dot kernel dot regularizer L1. You can actually have L2. L1, L2 is also there. L1, L2 means elastic net. See that? L1, L1, L2, right? L2. So these are the regularizers. In L2, right, there will be balancing parameter also. See the L1, L2. Okay, they gave ratios of L1, L2 separately. Right? They should have given one parameter, balancing parameter, right? I don't know. So L2, L1 regularization penalty is computed using loss is equal to L1 into reduce sum of absolute x, absolute value of x. Give me 1 second. That's it. See this here, the functions, right? Loss will be calculated when you apply. Let us look at L1 first. When you apply L1, right? Previously in 1.14, right? We had to calculate this manually. Okay, on the cost function, right? When we were defining this cost function, right? We used to define it separately, not like this. Okay, when we define the cost function, we used to add that additional term here, but in the new version, right, they changed it. So a loss is equal to L1 star reduced sum of absolute x, right? Absolute x. So what is L1? L1 is this thing. This term is L1. Okay, they are multiplying x with absolute x. That is the loss. So absolute x they are calculating, theta, not theta. What is x here? See, this is the problem with TensorFlow documentation. See, this had x. What is x? Okay. Okay. If you use, this is the point. If you use the activation regularization, right, x is going to be taken, the activation outcomes are going to be taken as x. Okay. If you use weight matrix, right, kernel regularization, weight is going to be taken as x. Okay. Got it? Should I repeat? So this is the regularization term, right? We are calculating this regularization term. Okay. So loss is equal to, I think we should add that loss plus, right? Loss plus, maybe L1 is the whole term there. Whole term, then how will they multiply this also into MSC? Did you get my concern? Did you understand my concern? Guys? Guys, did you understand what I'm actually talking about or what I'm thinking of?
Yeah,
No?
instead of adding the component, L1 component is actually trying to multiply.
Multiply. So basically L1 component is this one. Okay. There is loss, right, plus L1 component, we were actually doing it. Okay. But here they took the L1 component, right? L1 component, maybe they took it like, this part they are calculating, I think. This is the reduced sum of that whole x is this part. Okay. They are taking L1 component is lambda by m, I think. Right. This part they are calculating. Let me show you that. No. Let me show you that. So L1 is the lambda by m or whatever, right, into reduced sum of x. What is x here? X is the thetas are the outcomes of the activation functions. X is the thetas are outcome of the activation functions. So here, right, that's the part they calculate. If you look at L2, it's going to be squared. reduced squared x. Got it? L2 star reduced sum, we'll see why L2 star we'll see later, but reduced sum of squared x here, reduced sum of x here, absolute x here, right? Those are the terms there. Absolute x lasso.
That's correct only, right, sir?
Yeah.
So L1, L2 are the hyperparameters, and it is trying to multiply L1, the absolute or the squared values. So
Yeah,
here
this
also
part.
lambda is the hyperparameter. It is multiplying the sum of absolute values or sum of squared values.
Yeah, sum of squared values or sum of absolute values is okay.
But it is multiplying it here also. It is multiplying the hyperparameter. This MSE of theta is not given there. It's only
MSE of theta. That's the concern. I was actually that's the concern I was actually having. So when you apply the L1, L1 loss, right? Maybe that loss will be by default present, and then penalty. L1 regularization penalty is computed as. So penalty, when they say, right, they're going to add this term to actual cost.
actual loss. Yes.
Yeah, penalty they are saying. So that's the point. So this is good, right? Now I am clear actually, right? So I said that there is a kernel regularizer and then activation regularizer. When you apply regularizer, right? How will you know that it is doing a activation? Using a activation outcomes, or sorry, trying to constrain the activation outcomes, or the weights will be decided by the parameter there. Kernel regularizer will take weights as x. Activation regularizer will take activation outcomes as x. Got it? I'm clear now. Got it? I can actually answer if you have any question now. There
So
is
when you say activation outcome, what exactly is it? Is it only a single value coming out from the neuron?
4 values, right? In this layer, all 4 values, four values. Maybe it's going to take all the activation values and then apply it onto the final whatever cost function. There is a cost function plus regularization term, right? See, if you see this here, there is a cost function plus regularization term. How do you calculate cost function? Y cap and y should be there, right? When are you getting y cap? Here, right? So when you are trying to apply regularization, right? If it is a kernel regularization, all these weights will be taken, right? All these weights will be taken, and then you apply, absolute value or square along with cost. Okay. If you are doing activation regularization, right, you will take all the activation values and then apply square or absolute value. Got it? Got it? No?
Kernel regularization is fine, but activation.
See, kernel regularization, you are taking all the weights here, all the weights here, all the weights here, all the weights here, and then doing absolute or squared, depending on L1 or L2. Okay?
Yes.
Similarly, activation also, you will take all these, and then put them into the absolute or squared, depending on L1 or L2. Got it? Right? Clear, right? No? Okay, you got it, I think. Okay.
Yeah, I will check how what I will need to understand more on the activation.
Yeah, I'll reiterate one more time because same thing is happening in deep learning also. Here, how do you calculate MSC? You take the outcomes, right, y caps, and you take y's and calculate mean squared error. Right, this is linear regression, but in logistic regression, it's going to be cross entropy, right? When you calculate cross entropy, you need h of x 1 by 1 plus e power minus z values, right? The probabilities, and you take y cap and try to put them there, right? Y cap and put them there, right? So, and you are actually taking all the thetas which are involved in calculating y cap. Same thing you do here, right? You calculate the cost function cross entropy. To calculate cross entropy, you need y cap, which is given by the last node, right? And then you need all the weights involved in calculating y cap. Those are the weights here, the kernel weights. You take all of them and put them and put 1 to whatever, right? So here 1 to n, because there are only n parameters, right? n input variables. So you will have n thetas. But here for each node, here 4 3 is 12. Here 4 4 16. Here again 3 4s, right? Whatever, that whole thing we will actually try to square and sum. That is kernel regularizer. If it is activation regularizer, right? 1 2 3 4, right? 1 2 3 4 4 4 12. 12 activation outcomes will come in this place of theta x. They said x here instead of theta. It can be theta, it can be x, depending on which kind of regularizer you are using, kernel regularizer or activation regularizer. I hope I try to demystify a little more. Have a look at it, you will get clarity. Definitely you need to look into that. Definitely. Okay. So how you do it, how do you do it? In a dense layer, you have number of nodes, activation function, kernel regularizer or activation regularizer, and the regularization class L1 or L2, and then the alpha value, right? In regularization, right, we call it as alpha. So I think where is the parameter here? Yeah, see this L2. So they changed the variable name here. If I run this code, right, it will throw error. So, from L, they changed it to L2 and L1, I think, the variable name. You run the code and see. I already uploaded the files there. So they changed the variable names here, L1, L2. Previously, it was L only. Okay. So,
Sir, if you use that kernel and active both same time, sir?
well, we can. When the model is not coming down, right? It is overfitting on the train set and not fitting well on the test set. You can apply all kinds of regulations at once. But no, when you apply all kinds of regulations, right, model will not work at all. You can apply kernel, activation regularization, bias regularization. On top of it, dropout also you can apply. I'll explain the other way of regularizing the model now. So you can apply all at once.
Then how will you take the values or weight values? For example, kernel is applying on the terms, right? So after the node output, we consider as active, right? Right? But here the kernel will apply that regularization. So it will take that value after kernel apply the regularization or before that.
Sir, when we say regularization, right, we are calculating y cap. First we are calculating y cap and we have cost, and then we are applying it, right? That means one iteration is over, completely over. You have taken some random weights, or maybe maybe thousands of iteration it is. You don't care. You have all the weights here, all the multiplications, linear combinations happened, all the sigmoid calculations happened, and you got y cap. Now you have all the outcomes and all the weights. You can actually take all the weights, square them and sum them to the cost. Additionally, you can plus, right? You can add all the activation outcomes and square them and sum them. Got it?
Okay. So
that's a good question. Actually, you are actually thinking, right? When I'm applying regularization, how can I get activation? Right? The kernel regularization, how can I get activation values? No, you will have everything. At the end, you are applying regularization. At the end of every iteration, you are applying regularization. Clear, right? When I say at the end of every iteration, you have all the weights, all the outcomes also.
Yes, sir. Yeah.
I think Seshiram also had that doubt, previously when I was actually talking, right? No?
Not exactly, sir. I was confused about the number of outcomes coming out. If it is the weights, it from.
So number of outcomes, why are you confused? There are 12 nodes, so there will be 12 outcomes, right?
No, that later on I got clarity.
Yeah.
So weights are the number of weights from each node. Outcomes is one outcome from the node. That I got the clarity later on when you told.
Yeah, good. So in this network, right, in this particular network, if you apply kernel regularization, it's going to be 4 3 is 12, 4 4 16, that is 28, and then 3 4s, right,
40.
12,
12.
that 38, 40, 50, and then 53, right? 53 thetas will be added. It's a kernel regulation. Plus, if you add the activation regulation also, then you will have same kind of term here. Plus lambda by m 1 by 2 sigma I is equal to 1 to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I activation squares. Got it? That's how the cost function is going to be. We'll have additional penalties of theta squares and the activation squares if you add both at once. Okay.
Yeah, got it, but instead maybe they have complicated it.
Yeah.
So instead of adding one more activation regularization, the lambda can be adjusted, right?
Maybe this is all right, trial and error kind of a thing, right? The deep learning, first they found ensemble models, and they are actually trying to exaggerate this ensemble model thing to make the model too complex. When the model becomes too complex, right, they would have tried to regularize using only thetas. It would not have happened, so they added additional terms also. It's all research work, right? So we don't know. Maybe while playing with the code on a data set, we may know the importance of it. Lambda, we may be playing with between 0 and 1. Still the model is not, overfitting is not reducing, then they would have added this. We don't know. Yeah. I think your idea is right, but they're complicating it, and it is like, giving you the complete flexibility of what you want to do. In a machine learning algorithm, whatever the algorithm, the equation is there, you can just use that equation only. But in here, right, you can generate any equation you want. Yesterday I showed you the model class, right? The sequence class, the sequential class and model class. With model class, right, you can create a network with too much complexity. When you are creating a network with too much complexity, the function you are changing. When I say the function, if you look at this whole network as one equation, and by the time it reaches here, there is a very complex equation, right? So you can create an activation function or an algorithm with a complex equation. Got it? So that's the flexibility given. In machine learning, that is not there. That's where deep learning is more powerful and more popular. Okay, so we need to think in that way. That is about L1, L2 regulation, and the elastic net is also there. L1, L2 is the elastic net. So next regularization is dropout regularization. So here we are actually trying to play with the weights or activations to drop some of the nodes. But there is another concept called as dropout regulation, where you can specify the percentage of nodes you want to drop in a network. Okay. So I have taken keep prob here because initially when I wrote nodes, right, that time there used to be a parameter called as key prob, or in theory it used to be key prob, but now you have dropout hyperparameter. So let me try to, I think there's a code, so that's better. See this here, I have taken a dense layer and then I am specifying dropout 0.2. That means I want to drop 20% of the nodes randomly. I'll show how it works in a moment. But you know, I have taken 128 nodes. But when I took this kind of a network, right, the model may be overfitted. So initially the network was like that. Right? Initially the network was like that. So the commented out things were not there. Let me take out these. Initially the network was like that. The model is overfitted. I might have tried the L1, L2 regularization, but still model is not getting fixed. Maybe activation regulation also added. Still model is not getting fixed. Still it is overfitted. Then you can add dropout regulation. In a particular layer, you can drop. So why do you need to drop? You know, you can take 20% less nodes and build a model, right? So 20% less means 10% means around 12.8, maybe 13. 26 nodes you can reduce and then say 1 or 2 here. Right, 1 or 2 here and then play with, then run the model. But why are you using dropout? Because this is a hyperparameter. You can actually, you know, there is a in Keras, right? There is fine-tuning module is there. I forgot the name of it. Like grid set CV. Now I'll implement that and show you maybe by Monday. Right, like grid set CV, where you can actually change these hyperparameters and it will give you the best model. Right, instead of you changing these weights manually and trying to execute, if you have a dropout, right, that actually does it, that's going to be better. The second thing is, in dropout regularization, it is not going to take fixed 1 or 2 nodes there. In one iteration, right, it may drop 20 different nodes, and in another iteration, it may drop another 20. So that way, right, it is actually trying to make the nodes equally powerful, no, randomly equally powerful. So let me try to show you how dropout works, and then you will understand what I'm actually talking about. So key prob, now I took, you know, this is the reverse of dropout. So if I say key prob 0.75, dropout is going to be 0.25. Key prob 0.5, dropout is going to be 0.5. Okay. So how it works is, say the iteration 1, and Sami part, you don't care, and hidden layer 1, right? When you say dropout is equal to 0.75, how it is actually working on hidden layer 1? It actually takes a matrix like this, a vector, right? A vector with zeros and ones. I said key prob 75 or dropout 0.25. So it will randomly choose 0 at one place and 3 ones. Out of 4, 0.25 means 1, right? So at one place it will take 0, the rest of the places it will take 1 and multiply. Multiply what? Multiply the activation values. So there are weights here, okay, and then you multiplied those x's, you got activation values, and those activation values will be multiplied by the random ones and zeros depending on the dropout value, and you got these values now, right? Now you calculate inverted dropout activation values, or the network will calculate inverted dropout activation values. That's going to be 0 divided by what is key prob, 7 divided by key prob, 20 divided by key prob, 5 divided by key prob. This is the outcome, right? It is going to output for the first node, the activation value is going to be this one. Second node, the activation is not 7. This is going to be the activation. This is going to be activation. This is going to be activation for fourth node. So inverted dropout activation values are the values going into the next layer. When you apply dropout, what we did, we nullified one node and we tried to add that whatever nullified value to the other nodes. So when you actually did this, you know, inverted dropout, right, you see 42.64 you got. 42 is the actual before applying dropout, 42 is the total of the activations outcomes. After applying inverted dropout, you are actually trying to create the same situation, but you dropped out one node, right? So that's how that, you know, the dropout activation works, and this is going to be the, after applying dropout on the first layer, this is the outcome. Now you are applying second layer 0.5. When I say 0.5, right, it randomly chooses zeros and ones like this and then multiplies the activation values and calculates inverted dropout activation, takes this. But here see, the total before and total after were not matching. That means, 50% may not be right, but we never know. This is a trial and error thing. We call it as hyperparametric tuning, but it's a trial and error thing. If model works at 0.5, keep prop, we'll keep that as it is, even though this is not matching. But generally, you don't know what is happening before and after on the activation outcomes. But in theory, right, whoever created this deep, the dropout regularization concept, they mentioned that making sure that the before and after scores are close to each other, applying dropout will make the model, reduce overfitting and work the same way, right? So that's the theory. But it's a black box. What is happening inside a neural network? If you take 10 layers and each layer having 20 nodes, it's going to be 200 nodes, and you don't know, right? There are many weights in there. You don't know what's happening where, right? So it's all black box. But theoretically, to understand, right, it should be kind of close to each other, total before and total after. Then the model will reduce the overfitting and work best on train set, test set, and all that. So on the second layer also you applied inverted dropout. This is how it became. So now the network is like this. So when I made this activation 0, activation 0, activation 0, the network is like this. Okay. First iteration, when you apply dropout regulation, the network is like this. Okay. So there is one question I have. I am showing you network like this. What happened to these weights, and these weights? So some weights are missing, right? What happened to those weights? Are they there in the matrix, or are they completely gone? In the weight matrix, did you get my question?
I think they will be there with zeros.
Yes, they'll be there. Weights will be there. But because of making the activation 0 and calculating this inverted dropout, the effect is not there. These weights are going to be there, right? The outcome will not come. The effect of these weights will not impact the network. So this is just impact diagram. No, it is not physically removing these weights and these nodes. In the next iteration, right, it is actually choosing these numbers randomly. It may make this number 0 and these 3 ones. That time, right, these weights will work again. Okay. In the next iteration, this one may become 0, this one may become 0, but this may become 1 and this may become 1. That time what happens? These nodes will have affected and these other nodes will become 0. Got it? That's a key point we need to understand in dropout regulation. Got it? This, the drop, the dropout multiplier vector is generated randomly. When it generates randomly, effect of some nodes will be there, effects of some nodes will not be there. Okay. So bottom line, what I am trying to explain is all weights get strained randomly, some at once, some at other times. Got it? All weights in a neural network get strained, some at once and some at different time. See in the next iteration, right? I have chosen a random, dropout multiplier where 0 is here. So this time what happens? This node is gone. Okay, this node is gone, right? On the second one also, see first 2 are zeros and second 2 are ones. So now what happened? These 2 nodes will go, right? These 2 nodes will go, and so this time these weights got trained. So when you apply dropout regularization, randomly it chooses the nodes it need to train. That way, at one iteration, some nodes will get trained, and in other iteration, some nodes will get trained. In a way, some weights will get adjusted in one iteration, some weights will adjust in another iteration. That way, you are not having total network's impact on the model, but ultimately at the end, you will be using total network. It is not going to be like this, bits and pieces network. You are going to use total network because at random you trained all the weights. You got the point? At random you trained all the weights. Right? In production and test you should be using all the weights. While training, you may not use all the weights, but in test and production, you will be using all the weights. Got it? Dropout regulation, did you get it?
Sir, in reality, the iterations will be only one, right? I mean, the epoch.
Many iterations. Many iterations. See this network. Many iterations in there. See this here. See epochs I said 10. Right? If I took batch 32, in our data set, in the train set, I have 33,000 records. That means around 1,000 iterations will happen in each epoch. With each iteration, 32 records taking. Right? That's also random. Right? Randomly, it will pick 32 records in each iteration, and 1,000 iterations will happen one epoch. There are 10 epochs. That means 10,000 iterations will happen on this digit recognizer data set. Got it? Got it? No? Confused?
This is a kind of cross validation, right? So these epochs and batches we are applying to check where which parameters are better.
No cross validation. It is a gradient descent algorithm. You just try to keep that gradient descent in your mind. Whatever I explained. If you forget, right, just go back to it and try to watch that video. If you need a recap, right, I'll do it in 10 minutes, maybe tomorrow, right? So you always keep that gradient descent in mind, stochastic gradient descent and gradient descent in mind. Same thing we are doing here in a bigger scale. Sir, any questions? Girigaru or Narayana, any questions?
No, sir.
I have only one small question, sir. The model.fit, we are giving the X-train and white train dot values. Why we are giving white? This you said that it's NumPy array.
Yeah. X-train is already converted to NumPy because when we did train test split, right, it actually got converted. If you look at the type of it, right, it's going to be, I think this is also, I don't know. Maybe you check it out. You check it out. Maybe it throws some error. That's where I kept values. I think it should be NumPy array only, but on an NumPy array, you should. I think this is this is data frame. Maybe this is series object. Okay, so maybe in the previous version, right, it would have taken data frame as input. Here also data frame it would have taken. This is data frame, but this is a series object maybe. That's where we have to say dot values.
Okay.
It is not taking. It was not taking series object. Maybe they would have fixed it. Try taking out and run. If it is working, that is good. If not, right, take dot value. NumPy array or data frame it is taking, I think.
Okay, sir. I'll check.
Try to check the type of it, so you'll know why. Depending on errors, right, I would have changed some things here. So, out of no reason, maybe. Yeah. So this dropout regularization, right, it is very powerful and we'll use it, extensively. The point we need to remember is don't use key prob in production, right? This is not, relevant for 2.0, TensorFlow 2.0. In previous versions, right, we used to manually give this value, key prob value or dropout value. We used to give manually. That's where we used to take the placeholders. We used to have placeholders, kind of variables there, where you pass 0 when you are doing test and production. In the training, you pass some 0.2, 0.3, some value like that. Okay. When dropout is applied, parameters in cost function change randomly as some of the intermediate nodes get dropped out randomly. Due to this reason, first build model with no dropout. Anytime regularization you apply when model is overfitted, right? So this point is not needed, but as a caution I put it, and in interviews they will ask, will you apply regularization, dropout regulation right, right from the beginning. No, we will build a model, we see how it's working. If it is orbiting, then we will choose either L1, L2 or dropout, or all of them at once. Okay, so that's the point you need to know. But many a times interviews will not happen this intense on deep learning. They'll ask many questions on machine learning, but when it comes to deep learning, right, people are afraid to touch deep learning. Okay, but we are not, because we know it is very simple. It is very simple. Believe me, it is very simple. You would have already got the gist of it. If you know gradient descent, stochastic gradient descent, how it's working, that's it. That's the that's the end of deep learning. Okay, so I think I'm conveying it well, but I don't know. So you to apply dropout regularization, right? You should be applying like this, or even in dense also you have some variable. I think dense layer also there is some. Yeah, dropout is not there. Regularization dropout is not there. Okay, so you need to add an additional layer, dropout layer it is. So what is happening is you do the activation calculations, you pass it to dropout layer. In the dropout layer, it is calculating these things, right? You calculated these activation functions, you passed it into dropout layer, it is taking the dropout multiplier, multiplying it, calculating the inverted dropout activations, and that is taken as the output. So I should have kept this layer and then a dropout layer where it is so into dropout layer, right, only one will go. This will go into this, right? This will go into this. This will like that. It is, got it. So the dropout layer is basically calculating inverted dropout activation values and passing them to the next layer, calculating activation values, calculating inverted dropout activations, passing inverted dropout, and then passing it to the final layer, output layer. Got it? So you don't want to apply dropout for 2 layers, you want to apply for 1 layer, you can do that also. Okay, so that is the regularization, right? And tomorrow we'll actually look into vanishing and exploding gradients, a concept where we need to carefully initialize the weights. There are pre-built values in the pre-built approaches in the neural networks which will anyway carefully assign the weights, but why it is needed we need to understand. Exploding and vanishing gradients we'll understand, then we'll understand the different advanced optimization techniques. We have seen gradient descent, stochastic gradient descent, right? We'll see momentum, RMS prop, and ADAM, 3 advanced batch normalization. Okay, 4 advanced optimization techniques, and then we'll know order of playing with hyperparameters. Okay, by tomorrow we will get full grip on deep neural network. Okay, you can do regular classification, regression, anything on deep neural network. Okay, weekend we'll try to have some class and some practice kind of a thing, right? Saturday, Sunday, if you are at least one day, right, either Saturday or Sunday maybe, if you are not comfortable with both days, right? And then from Monday we'll start CNN. Once CNN is done, we'll jump back to NLP. Okay, I'll show you the word vectorization, word to vec and glove and all that, and then I'll show you I'll give you one exercise which is pending for last 2 batches. See whether you can do it or not on NLP. Okay, so that's it from my side. Any questions you can ask.